I think we should wait for people to show up. Well, Iris, you're back. Is everything okay? I saw you disappeared and then reappeared again. Do you know if others are coming? Because if they are, we can wait for a couple of minutes. There's enough time. Okay, there you are. Perhaps we can start and then others may join, but do you know if we should wait or we should go? You probably have some unstable connection. That's why you're coming in and out. But do you hear me well? Do you hear what I'm saying? Please say something back. I see here there is no microphone next to your name. But okay, so can you type at least? Or maybe on you're on your phone or something. Okay, I think we can start. So the lecture will be recorded anyways, and then other two students can watch the video. So hopefully next time they'll be able to join. Okay. So last time we talked about linear systems of equations in general, and we looked at examples that a system of linear equations has either no solution or exactly one solution or infinitely many solutions. And this can be understood in terms of, so these are the following examples. We looked at system of two linear equations This equation here, 5x1 plus 6x2 is equal to 1, and x1 minus x2 is equal to 3. So this system has one solution, which can be illustrated by intersection of the lines that describe each of the equations in the coordinates in Cartesian coordinates. Then here's an example with infinitely many solutions when both lines are coincident with each other, so that they are the same. And finally, there's a solution. There's an example with no solutions when the solution is an empty set, right? So, and this happens when the lines are parallel to each other. Now, today we'll start with with studying the set of solutions of linear equations using matrix notation. Let's elaborate this using an example. So let's look at the following system of equations. Say x1 minus 2x2 plus x3 is equal to 0. Then 2x2 minus 8x3 is equal to 8. And 5x1 minus 5x3 is equal to 10. Right? So it is convenient to write the all the information in the system in terms of a matrix. So a matrix is a table. Here, the left-hand side of the equation of the systems of equations can be represented as the following matrix. It's 1 minus 2, 1, 0, 2 minus 8, 5, 0 minus 5. And then if we multiply this matrix by the column x1, x2, and x3, and using the rules of matrix multiplication, we will get the vector with components x1 minus 2x2 plus x3, 2x2 minus 8x3, and then 5x1 minus 5x3. Right? So this is the left-hand side of the system of equations, and the right-hand side can be presented as a column vector with components 0, 8, and 10. So therefore, we can write the equation, system of equations as this matrix multiplied by the column x1, x2, x3 is equal to vector 8, 0, 8, 10. So let's denote this matrix with A. So then we can write it as A multiplied by vector x is equal to vector B, right? Where A is this 3 by 3 matrix. Vector x has components x1, x2, x3, and vector B has components 0, 8, and 10. Okay. Now, it will be useful for the future reference to introduce the so-called augmented matrix of the system. So, augmented matrix will be the matrix of, in this case, 4 by 3 that will contain the right-hand side of the equation as its last column. So here the augmented matrix would look like this. It's 1 minus 2, 1, 0, 0, 2 minus 8, 8, and then 5, 0, minus 5, and 10. Right? So you can see here that this is the vector B, and this is matrix A. So this is called augmented matrix, right? So in this case, it's a matrix of size 3 by 4, which refers to first number refers to the number of rows in the matrix. There are 3 rows, and second number is the number of columns. Okay. Now we will use this matrix notation in order to solve the system of linear equations. And instead of just doing usual substitution of variables from one to another, we will be doing operations with rows of the augmented matrix. So, which will be equivalent to the elimination procedure that we usually do, that you are familiar with from high school. So from now on, let's look at the augmented matrix of the system. So now the idea is to get rid of is to reduce it to a certain form where it will be easier to find the solution. So to find the value of x1, x2, and x3. Right. So let's do it by. Let me return back the system of equations. Solution. So the question is to solve the system of equations. So one thing we can do, we can multiply the first equation left and right hand side, multiply it by 5, or rather by -5, and then add it with the third equation. So step 1, multiply first equation by -5, and add, meaning that you add the left-hand side to the left-hand side and the right-hand side to the right-hand side. This is an allowed operation to the third equation. Right, so if you do that, so we'll keep the first equation as it is, right? X1 minus 2x2 plus x3 equals 0, and then the second equation we copy, we keep it as it is. And the third equation, what we're going to get? We're going to have 0 plus 10x2 minus 5. Minus 10x3, right? Because it's minus 5x3, and then there's another minus 5x3. Is equal to 10. Right? Now, let's write down the, that's what's been done. Now let's interpret what happened in terms of the augmented matrix. We're just gonna write next to it the augmented matrix for the system. So I'm just going to write it down here. It's 1 minus 2, 1, 0, 0, 2, minus 8, 8, 0, 10, minus 10, 10. Okay. So we'll do each transformation step by step in terms of elimination of variables and also in terms of operations on the matrix. Okay, good. Now, what's the next step that we can do here? So second, we can multiply the second equation by a factor of yeah, so we can multiply the second equation by -5 and add it with the third equation. So multiplied by -5, right? So then we'll get what? We get x1. So the first equation we just copy, nothing happens to it. x1 minus x2 plus x3 equals 0. And then we can still keep the second equation as it is, and then with the third equation, we'll add it to the, so maybe I should write it here. So multiply this procedure is not unique, but later we'll discuss some algorithm that will help us to make it more or less unique. Multiply second equation by -5 and add to the third equation. So yeah, this one we keep. It's 2x2 minus 8x3 equals 8. Right, and here we have 0. Now -8 times -5 is 40, and -10 is equal to 30. So it's plus 30x3, and that's equal to 8 times -5, that's -40, and plus 10 is -30, is equal to -30. So the augmented matrix in this case is 1, -2, 1, 0. So the first row did not change. And it's 0, 2, -8, 8. And this is 0, 0, 30, and -30. So you can see that we're getting close, and then we can divide the second equation by 2. We'll multiply it by a factor of 1/2, and multiply the third equation by factor or divided by 30. Divide the second equation by 2 and divide third equation by 30. So that gives us x1 minus 2x2 plus x3 equals 0. And then 2x2 minus 8x3 is equal to 8. And here we get, oh, sorry, I forgot to divide. And here we get x2 minus 4x3 is equal to 4. And finally, it could have x3 is equal to -1. So you can see that essentially we have found the solution for x3. So that gives us the augmented matrix 1 minus 2, 1, 0, 1 minus 4, 4, 1 minus 1. Yeah. Okay. So now, so therefore, we have found our first solution, right, at the bottom. It's x3 equals -1. Now let's try to kind of go do the operation backwards, right? So we'll find now, we'll eliminate using the third line of the system, which is the shortest, subtracted from the second line and from the first line. But so the order here is important. Now we can multiply this equation by 4, right? And then add it to the second equation. Okay. And then we don't do anything with the first equation yet, right? We'll get to there. We'll get to there soon. So the first equation just stays again, x1 minus x2 plus x3 equals 0. And then here we have x2 plus 0 equals 0. Right? And then x3 is equal to minus 1. So in terms of augmented matrix, we get 1 minus 2, 1, 0, 1, 0, 0, 1, minus 1. Okay. So we have found x2 here, right? So which means that x2 is equal to 0. Okay. So we're almost done. Now we need to find x1. So for pedagogical reasons, let's do it again systematically by using operation with rows. So now we need to get rid of, so we need to find, we need to reduce the equation to the form when we have x1 equals something. How should we do this? Well, we can multiply, we need to do two things. We can multiply a third equation by minus 1 and add it to the first equation. So that will take care of the x3 coefficient. And then we multiply the second equation by 2 and add it to the first equation. That will get rid of the x2 coefficient. So step 5 here will be to multiply the third equation by minus 1. Excuse me. And add it to the first equation. And multiply second equation by 2 and add it to the first equation. So what happens here is this. So the first equation becomes x1 plus 0 plus 0 equals 0, excuse me, equals 1. That comes from the third equation. Second equation becomes, well, it stays x2 equals 0. And the third equation is x3 is equal to minus 1. And finally, the augmented matrix looks like this. So it's 1, 0, 0, 1, 0, 1, 0, 0, 0, 0, 1, minus 1. Okay, so that completes the solution. So we can write here that x1 equals 1, x2 equals 0, x3 is equal to minus 1. Right? And yeah, so it turns out that in this example, the solution is unique. Geometrically, it can be represented by having the 3 planes that are described by the first 3 equations here. So if you look at, let's look at the beginning. We can we can interpret each of these 3 equations as equations for a plane in coordinates x1, x2, x3. And then it turns out that these 3 planes will intersect at one point. Like so, let's draw those planes on a computer and see what's going on. So we'll get to mathematically in seconds, to the elimination procedure in seconds. So the here are the planes, right? So it's x1 minus 2x2 plus x3 equals 0. That's the first equation. Then we have x2 minus 4x3. Let's put it like this, right? It's yeah. So that's equal to yeah. Goes to 4. X. I'm not doing it. Not doing the original. Okay, so yeah, so it's like 2x2 minus 8x3 is equal to 8. And then the third one is 5x1 minus 5x3 is equal to 10. So let's draw them as if we're doing 3D plot. And now what we're going to do, we're going to write this. So we can solve them for x3 because these are simple equations. So I'm going to write them as such. We're going to draw them as a function of x1 and x2. So if x1, x3 is equal to, if this is satisfied, we can solve this for x3. So x3 will be equal to negative x1 plus x2. So like let's do it like this, right? So let's solve it for solve this equation for x3, right? So that's that. That's the first plane that we're going to draw. Then we're going to solve this equation for x3. Excuse me. There's no 0 here. Then that's another plane that we're going to draw. And finally, we solve that equation for x3. That's another plane. That's the third one. And then we allow x1 and x2 to vary between say, -5 and 5, and the same with x2. Here, each plane is drawn in its own color. Try to make it a little bit, maybe let's make it a bit smaller. From -2 to 2 probably will be a bit better. Yeah, so nevertheless, right? So I think that it doesn't really make much difference. You're going to make it a bit bigger. So you can see here that there's a point over here in the center, or not in the center. So we can see what the coordinates are. So we found the solution, which reads x1 is equal to 1, x2 is equal to 0. So this is x2 axis. It happens that x2 equals to 0. x1 is equal to 1, right? And x3 is equal to -1. So it's kind of hard to see here because the vertical axis is up. But let me change the range. And so range is -2 to 2. That around. 1 second. plot range. Yes, it's plot range. Yep, there you go. So yeah, indeed. So you see that there's a point here where all three planes intersect, which is located at 1, 0, and it's -1 in the z-axis in the x3. So here, all three planes, they intersect at one point, which is something that doesn't happen very often, and that provides you the uniqueness of the solution. Okay. Okay, good. So next, let's talk about this. I'm going to keep writing in Mathematica. Bigger here, so that the that's better. Yeah. So if you have any questions, let me know. Oh, we were joined by Wise. Yeah. So if you have any questions, just I'm not sure at which stage you joined. Or we have Wise and Iris. Hi, gals. Yeah. So do you have any questions about? Do you have any questions so far?
Hi, Wise is Lucia here.
Oh, hi, Lucia. Yeah. So somehow we had some problems with connectivity here. I think Iris was coming in and out, so I decided just.
Yeah. I think so.
Okay.
Iris, are you here? Are you able to connect?
Yes, I'm here.
Right. Yeah. So I think there are like 2 users, Iris, right now, which are maybe it's like a phone and a computer or something. But I'm glad that she was able to get in. Okay. Good.
Okay.
Yeah. So I sent email to everybody in class that we're starting, and regardless where we're recording, so it will be available to you later. Iris, do you have any questions? Okay, good. So, no, thank you. Good. Okay, let's keep going. Now let's talk about reduction of a system of equations to what is known echelon form. Right. So so we'll talk about this. So there are some practice problems in the homework, which I hope you guys will have a look. Well, let's look maybe at another example where solution does not exist, right? So that the planes do not intersect. So let's look at the system of equations. So it's like x2 minus 4x3 is equal to 8. 2x1 minus 3x2 plus 2x3 is equal to 1, and 4x1 minus 8x2 plus 12x3 is equal to 1. So let's write down the augmented matrix. I prepared this matrix here. So let's kind of swap it here. So we're going to write them here. So it should be 0, 1, minus 4 in the second column, 8, and then it's 2 minus 3, 2. And 1, and it's finally 4 minus 8, 12, and 1. And then let's continue doing the eliminating procedure. Only now, it's convenient when you start from top and then go to the bottom, right? To reduce the matrix to the upper triangular form, and then sort of to find the solutions, we go backwards, right? And then we have 0 here, which is a bit inconvenient. So first, what can we do? We can swap rows 1 and 2. Right, so we can do it like this. We just take to do it. I'm going to create 2 matrices. I'm going to swap them around. We are totally allowed to do that. Right? And then we can, so that's done. Now the next step was to multiply the first row by -2. And add it to the third one. So Iris, maybe you can tell me which matrix, what we'll get instead of the third row. Can you give me just, can you write me the 4 numbers, which we'll get? Okay, yes, first is 0. What's next? Yes, so yes, -2. What should we put instead of 12? 8 and -1. Yep, that's right. Yeah, that's right. Yeah, so we're getting there. Now, well, third step, we'll do the same. Now we keep the first row out, and then sort of work with the second and the third, right? So we multiply second row by 2 and add to the third row. And so what can you tell me the numbers after that, after we've done this? Now there will be 3 numbers. So this will be 0, right? It's by design. Then this is also 0. And here we have 15. Yep. So we see here 0 and 15. And then, well, it looks like there's a problem here, because if you actually want to write it as an equation, it will tell you that 0 is equal to 15, which is inconsistent, right? So like the last row implies that there's it's equivalent to the statement. So in other words, the whole system of equations is equivalent to the statement that 0 is equal to 15, which is inconsistent. So therefore, the system here has no solutions. Question?
No.
Good. Yeah. Are you familiar with this stuff? Like, have you learned it elsewhere, or if you know this, we can move on to something else, or is it new to you? Set to a little bit. Oh, I see. But not all of it, right? Okay, good. Yeah. So then just it will be nice that you can review and everything. So then you can draw. I use calculator in exam. You mean like graphing, like solve, like you use calculator to solve the system of equations, or what? Okay, yeah, so in this class you will not allow to do that, but so you should use the symbols, like you should use this row elimination algorithms to solve it. Right, so let's draw again this set of what happens in this case, right? So we have now let's solve it for x2. You're just going to draw 3 planes again. So that's the first plane, then that's the second plane. Oh, by the way, are you familiar with the software? It's called Mathematica. If you don't have the program, there is a website. It's called Wolfram Alpha. I'll show it to you in a second. So you don't have to have this program to do these calculations. You can do it online. And I recommend it against any other calculator or any other software that you know. It's really powerful. I use it for my research as well. Yeah, that's right. It's called Mathematica. Yes, Wolfram Mathematica, and then you should have a student like from your institution. You should have a student account or something like that. Okay, and then finally we need to solve this equation. Where is it? You can also draw them parametrically. So here there are 3 planes, and they clearly, like, if you look at them from this, well, probably need to do the range a bit more. Maybe it's 3, 3. But it's clear that they do not intersect at one point, right? Like the orange, green, and blue, they intersect each other, like they intersect pairwise, but never do they intersect at the same point. Yeah, so that's why there is no solution. Okay. Right, so just while we're at this Mathematica, so there's also what's called, if you do it online, you can go to this website, Wolfram Alpha. So like if you say traveling somewhere and you don't have access to a computer or whatever, if you go to this website, there's I'm not sure how it works in China, but it should be fine. And then you can just copy you can use the same syntax, the same language that I used, and it has online engines, so you can do the calculations. Sure, yeah. So in fact, if you learn how to use Mathematica after this course, it will be already a good, big achievement, I think. And then it's time well spent. Yeah. Okay. So, for example, like the homework that you're doing, of course, you're encouraged to check your answers, right? So, I still you still need to do the calculations, all the calculations by hand, or like in the notepad, and then the TA will grade this, but you can always check it, check the validity, check the correctness using Mathematica. Okay. So okay, I think we can keep going with keep working. So we'll get to Mathematica in a second. I just want to write a couple of things on the page. Okay, we put stop sharing here, and we go back to the notes. So our next story is matrices of echelon form. French word, that's why it's spelled with CH, right? Of echelon form. Now, what's a matrix of echelon form, right? So, for example, matrix that we had at one step in the previous example here. So this matrix here, if you restore back all the zeros, so this matrix is of echelon form. So I'll write the definition in a second, but basically, the intuition behind is that it should look like a staircase, like inverted staircase. So such that underneath the staircase, you should only have zeros. So in sense, like the longmost row without zeros should be above, right? So that's why in the second example, which we just did, first thing that we did was swapped the first and second arrow, right? Excuse me, first and second row for this to happen. And then sort of the next longmost row is beneath it, and so on and so forth. So this is the matrix of echelon form. So another example of a matrix in echelon form is, for example, 5, 7, 0, 8, 1, 5, 0. Again, and then the rest are zeros. And so that does look like a staircase. So the steps can be bigger, they can be smaller, but yeah, so that's also called echelon form. It's of echelon form. So let me give you a matrix which is not of echelon form. So 0, 0, 1, 1, 1, 1, 5, 7, 1, 0, 0, 1. So this is not. Yeah. So more formally, echelon form requires the following statement. So so first, all non-zero rows are above any rows of all zeros. Like in this example here, here's a row with all zeros, that it must be below all rows where there is at least one non-zero. Yeah, so when I say non-zero row, it implies that at least one element in that row is non-zero. So these guys are above any rows with all zeros. Okay, rule number 2 is that each leading entry in a row is in a column to the right of the leading entry of the row above it. Right? It's it's a mouthful. Let's see what it means. Leading entry, I mean, is this one. Say here. Right. So each leading entry. Yeah. So again, so each leading entry of a row is in a column to the right of the leading entry of the row above it. So if in the second row the leading element is 1, then it should be to the right of the leading element in the first row. Right. So this 5 is towards the left from 1. Basically, that's just a fancy way to say it. You have to have the staircase. Right. So you're not allowed to have stuff like this. Right. So here, this matrix is not of echelon form because this 1 here is to the right from that one. Yeah. So each leading entry of a row is in a column to the right of the leading entry. Of the row above it. Okay, that's rule number 2. Rule number 3, all entries in a column below a leading entry are zeros. All elements below, or all elements in a column below a leading entry are zeros. And of course, this is the case here, right? So this is the leading entry, and then we have zeros here. This is the leading entry, we have 1 0 over there. Okay, so that is called echelon form. And then on top of that, we'll also talk about so-called reduced echelon form. Which on top of this, on top of this 1, 2, 3 above, also adds here number 4, is that the leading entry in each non-zero row is 1. And 5, each leading 1 is the only non-zero entry in the column. Non-zero or non-trivial entry or element in its column. So we already had this reduced echelon form in the example above. So this matrix over here is in fact in reduced echelon form. Indeed, so clearly we have this staircase, and everything below here is 0. So we can check that 1, 2, 3 and hold. 1, 2, and 3 hold. Number 4 holds because leading entry in each row is 1. And finally, number 5 holds because everything, all other elements are zeros in each of these columns where we have the leading entry. So in general, a reduced echelon form. So an echelon form, matrix with echelon form would look like this. I'm going to draw it here. So it will be some, I'm going to draw it for me with some staircase. And then here it will be something else here, something else there, something else there. And then here will be something else. So here are all zeros. And then the rest is filled with some elements. We don't really know what they are yet, but they can be 0, they can be non-zero. So this is echelon form. And reduced echelon form would be something like that, right? So again, we have a staircase. So we have to have 1 here. Like 1s are in this leading position, and then all elements in the same column where these ones are 0, right? So elements in this column are all zeros except 1. Elements in this column like that. So everything else is 0. So not only below the staircase, but also above that one, right? And the rest is whatever it is. Okay. So why do we need this reduced echelon form? Well, once the matrix have been reduced to this form, it's easy to find solutions for the system of equations, right? And then we'll look at the reduction algorithm next. Okay. So I think at this point we can make like a 5-minute break, okay, and then we'll come back. We'll come back soon. Does it sound good?
No problem. No problem.
Sure. See you soon.